again, for this example, we try to solve for this one. This is the symbol we use for Venant working functions. And here is we have to do the hard work, okay? And we have no way, but we just directly deal with the differential equations. And from here, that is the first one come to my point is this. To talk about which format will be easier for us to pick. So for this example, you can see rectangular shape. It pretty much have a very easy boundary to check. So for example, we look at this side here. For this side, it's our normal vector pointing to this direction, which n has component 1, 0. So if you take Ln component, that means this one will be easier. So for the right side of the boundary, L equal to 1, n equal to 0. So you can easily have this one be explicitly expressed. So for this case, corresponding to this side, the boundary condition is like this. In a similar way, on the left-hand side, it's normal vector n pointing to here. So that means L equal to -1, m equal to 0. So here you plug in L equal to -1, 0, then you can have the boundary condition described here. In a similar way, the top and the bottom. Okay, so that kind of the handwritten, I put these things. Basically, that is I think this one and to similar to that one. Okay. So right now we have graphical representations of the problem domain, and we know on the four sides we have such appropriate boundary conditions, and then we can do something and try to convert this kind of problem into the standard template, the standard form of the Laplace equations. Right? Okay. How to do that one? In the appendix of the notes, I provide you one of the methods, and there's more than one solution process. The approaches can be used for this one, but that in the appendix I give you one. So without the details, and we can try, is this. After solving these equations, Laplace equations with the boundary conditions on the four sides, okay, and I think that is worth more than one page of the calculations. And again, for this one, I will borrow your effort from another class. So assuming you know how to do this one, then we can solve for sides. Once side is solved, then you plug into the stress component, which means you solve for the strain. Then with the strain, you determine the stress component. Everything will be eventually like this. Okay. From the beginning of the solution process to this step, just in terms of writing, if you know the solution process, just in terms of writing, from the beginning to here will take about 20 minutes. Okay, just in terms of writing the equations, that's kind of time rigor. So I'm going to skip off quite a few detailed, unrelated mathematics, and that one here. And so here we are able to answer the stress is like this one. And so once we have stress, then we are able to integrate these things. Okay, in that integrations, again, we have solved the function that is the function of x and y. Then we do a very rigorous the area integral over xy of xy over the cross section of the rectangular cross section here. And again, here you have to do the very detailed calculation. I believe I also copy and paste my calculations into the appendix there for your reference. Okay. And again, from here to here, that would take another maybe half hour just in terms of writing carefully. So here we solve for everything just like this, and we look at these contents in detail. On the left-hand side, the T is a given torque. Okay, that's a given numbers. And AB appeared here is the dimensions of the shaft. the shaft have the x dimension 2a. The shaft has the y dimension 2b. Okay, so here everything is in terms of dimension here. So G is a rigidity modulus that is given. So from this case, we are able to solve for beta, although that is a very complicated form here, but in theory we can do it. Okay, so so far so good? Yes?
All of that's just a constant.
Constant.
Except
everything,
beta, we're finding beta.
Everything is constant except beta. So beta we can solve it. So to this moment, we completely solving the problem. We solve the side first, then we determine beta through this equation. That is solution process. Good? Okay. Again, this one is obtained. This form is derived from this integration of this one. Basically, this kind of the massive form is from here. And in solving the Laplace equation over rectangular domain, like this one, they're going to involve, for example, the formulation, I can say the power series expansion or Fourier series expansions. And I believe the solution process I have taken is the cosine. The cosine Fourier series expansion in x directions, and then in y directions, we have a transform. Okay, so basically here the solution process is in terms of the trigonometry, the infinite series of trigonometry expression here. So that is the reason why we have this one here. Okay. This one I will want to make one more format, and I believe this one also be on your handout. And sometimes, again, sometimes people like to tabulate. The people like to tabulate the number to replace such a long writing. Okay. And so basically the people depends on different aspect ratio of A to B. They come up with K2. K2 is a calculation number simply by calculating this one. Then they put into this format here. And this is more practical, and I'm going to introduce this to you. Again, K2 multiply this number equal to, you can make this one, so basically the whole number divided by 3. Okay, so that is the 1 equal to this, and the specific K2 by definition is this one. That's it, nothing special. We just make the definition of the new numbers and then make K2, let me see here. Okay, so that's the K1. K2, yes, okay. So here from the previous calculations, our T equal to G beta, and that is the number. This one basically replaces all the messy, very long term. In terms of calculation with respect to different aspect ratio, that is the numbers. Would that be good? So that means, for example, for this number, that means B over A. So rectangular shaft will be something like this. So this is a rectangular shaft. In terms of our coordinate, we take the x in the narrow dimension, y is in here. So that is something like this one, okay? And for that case, K2, I can tell you if you have the pen with you, K2 is actually equal to 16 over 3. Okay, so this number, exact number is 16 over 3. Okay, so, and this number do have very important applications. And I'm going to take this last one, because usually in our practice, we always looking for the extreme scenario. This is one case, and this is another one. Okay, so keep this in mind. Right now, we are able to tabulate K2 from here. And let me go back a few slides. Let me explain what is K1. Okay, so again, the K2, we using the K2 to replace such a long terms, and we replace such a lengthy calculation in terms of the tables. If many times, say if you don't have or you don't access, you cannot access this formula from tables, if you interpolate the numbers, that can be very good estimations. again, if this formula wouldn't be available to you but the table, then you can use the table to interpolate the numbers. Okay. So once we have that one, then we begin to determine the stress. Okay, so for this one, and again, we have the stress in the previous page. I think I'm going to download this again somewhere. Nice. So again, here we have stress being calculated, and stress is something like this one. Okay, so here we are able to use program to plot the contour of the stress components. Good, nothing special. Just implement here. I use MATLAB. Okay, and here this is for each quadrant. I specifically plot the right direction of the stress component. For example, in the first quadrant, the ZX component is like this. The ZY is like this. Okay, in terms of the magnitude, because I have calculated, I know that in the first quadrant I calculated tau ZX is negative. Negative, that means direction must be going that way. In the first quadrant, this component is positive, so I know that it's going upward. Okay, so those one, I specifically identify the correct directions of the stress component. From here, you can see this one will help you to check your calculation will be correct or not. Because after more than 1 hour and a half to reach such a good result, of course, you want to make sure your result is correct. From here, I'm going to qualitatively give you something to check. For example, if you visualize this as a vectors, their resulting vector is something like this. Okay, and schematically multiply with this arm. Of course, this vector multiplied with this arm will produce equivalent torsion or twisting in that direction. The same thing to this point here. According to your labeling of the correction, the direction, that is the resulting vector force, multiplied with this arm again, resulting in this torsion. So in all the 4 quadrants, we have the torsion in the circulation the same as given. So this one pretty much tell yourself you are in the right track. Okay, you are in the right track. You good? Okay, so now we have the stress component. Then I'm going to calculate the magnitude. And the magnitude of the stress basically is given by this. The tau, the magnitude, because in our plane, for example, this is our xy, and here this is our x component, so tau z plane in x direction, z plane in y direction. Right now, we have labeled the plane on which the stress is there. So basically, that is a vectorized. Here we can pretty much tell in z-plane x direction square plus the z-plane in y direction square. From this formula, we determine the magnitude of the stress. And again, plug in the detailed formula here, taking the square and taking the square root of those one, and do that impatiently, then we are able to formulate, again, the magnitude in terms of very lengthy expression that is in, for example, something like this cosine and ax something, and very massive term there. Very massive term there. I skip it. Once we have a magnitude, of course, you can use MATLAB to plot the contour. And from the contour, you can visualize the maximum. But in the meantime, you can determine from this function, this is a function of xy. From this function of xy, you can also determine the maximum. Okay, and that one basically is a formulation come up here. So assuming we know how to correctly implement the maximum, then the final result will be like this. Again, we're using a symbol K1 to calculate such a lengthy terms there, okay? And to me, I think the calculation will be easier than reading those formulas, or the formulas longer than 1 inch is not for the formula. Okay, but I make a complaint here. So that is here, we're using K1. So K1 is the number regarding the maximum, the string stress. So that is the table here, okay? So here in this way, the maximum string stress basically equal to T is a given torque divided by, and AB are the half of the dimensions. Again, in our formulation for this province, this is 2A. Keep this in mind, okay? This is 2B, 2A, 2B. This is 2A, this is 2B. You have to know how the symbols be defined. And once we have a symbol be used like this, that is a formula. I also put the formula here for you to easily access. So I think this page will be most important, most practical for the future use. All the derivations we spend a couple hours to this moment is come to this table for the practical applications. This is the formula to determine the maximum stress. This is a formula to relate the torque between the beta. Beta is the rate of the twisting. All the calculations are related to the dimensions only, together with such a symbol K1, K2. So this one, again, this one is, what is that number? That is a kind of fraction. This is 16/3. This one I forgot. I leave that for you to think, but this one is exactly the fraction, some integer divided by some integer. I forgot it.
It looks like 8/3.
Yeah.
Maybe half of
Like half of the.
Okay, it seems you are smarter, so why not? Okay. So in this way, everything is so far so good. And again, we're back to our problem formulations. Since we know everything, and we with those tables, and since we know the stress, and we know how the shaft be twisted. So for example, say if I ask you what is the angle of the twist, say if I would constrain the bottom face, and given torque, and given dimension, given material properties, if I will ask you what is the angle of the twist here, how can you answer this number?
Just beta L, isn't it?
Yeah, just beta times L. That's it. That's it. Good?
So beta's units are radians per length.
Per length,
Okay.
yes, yeah. Good? Okay. And many times when students come to this point, they feel tired because it's been through so many things and so many rigors and so many formulations, kind of been confused. Again, I want to emphasize this is the starting of the important things to be applied, okay? And this one, I would say, don't waste the energy being learned so many stuff. We come to this is a slide here. The one final thing, and I want to tell you from the control plots, from all the evidences and been through, either graphically or either by the detailed calculations, and I can tell you the maximum stress happened at here and here. That is the middle place of the long dimension site. Okay? So for example, if we have this case, let me say, if we have the shaft like this, again, this is the X and Y. So for this case, A, B, this is 2A, and this is 2B. And since A over B is pretty big, so that corresponding is the extremal case, say 0.1, point something like here, we not listed. Okay, so basically that case corresponds to here. In this way, the maximum stress is here. Happen at the middle side of the long dimensions. If this is a torsion, then even you can identify the direction is here. Because again, you can utilize this is the force multiplied with this one that must have the same circulation of the torque given with the given one here. Be good? One more thing, one more time. This table gives you the calculation of the magnitude. From here, you need to tell yourself how to learn how to identify the directions. Together with direction with the magnitude, you can only uniquely, thus you can accordingly uniquely categorize the whole problem. You good? Okay. I think that is for the rectangular shaft.